Okay, so let's take a look at the conditions. We know that we have to get our data from a random sample, but here the normality condition, in a sense, is this. You may use this test when all individual expected counts are at least 1, and no more than 20% of the expected counts are less than 5. You can never go wrong as long as all the expected counts are at least 5. I would say that if let's say you have 5 categories. If one of the categories is less than 5, then you're still okay. But to be on the safe side, I would make sure that all the categories are at least 5. Then the condition will be satisfied, okay? Let me now show you how to actually do this computation. It's not really going to be expected of you, but just so you can have an appreciation of how it's done. The chi-square is created by taking the sum of each observed count minus the expected count squared divided by the expected count. Let's actually see how that works. I actually have it worked out for you, so I don't have to write it out. So let's take a look. Here we go. For Sunday, the observed count is 20, the expected count is 99. You would take the difference of those, you would square that, and you would divide it by the expected count, leaving you with this number. You would do the same thing here. This number minus this number squared divided by this number, and you get this value. The summation sign here that you see right over here means you add all of these together, and that gets you your chi-square statistic. Then you can go into the distributions in your calculator, the chi-square distribution, put this number in along with the number of degrees of freedom. Again, it's a number of cells minus 1. 7 minus 1 is 6. You could actually come up with your own p-value, but again, by and large, you'll be able to use the calculator to compute the p-values, okay? And again, it's the same condition that we always have. If it's less than 5%, we reject the null hypothesis. Okay, so that is the chi-square test. Let's take a look at this is what the chi-square distribution looks like. It really depends on the degrees of freedom. The bigger the degrees of the freedom, the more it's going to look normal, but it's still going to be right skewed. Okay? Let's take a look at another example to see how things work. This one is very similar. We want to say that the trick cereal is distributed, the different flavors in the cereal is distributed uniformly. Now, this is when we actually bought a box, this is what we counted, but let's actually see if this is uniform. So our null hypothesis is always going to be the distribution, the p-value for the grape is equal to the p-value for the lemon, is equal to the p-value, and put an ELE and an LI for the lime, equal p-value for orange equals p-value for strawberry. Probably better yet, you might say in this particular case, all flavors are uniformly distributed, and the alternative is at least one flavor is distributed differently. Basically, P of G doesn't equal P of LE, etc. One of these is different, okay? So, how do we do this? You go into your, you have to go to your lists. You're going to go to Edit. I'll clear out these lists. Okay, so what we have here is 530, 470, 420, 610, 585. I'm actually going to find out how many there are there. So we have a total of 2615. So I'm going to take each one of those values and divide it by, 2615 is the total. Okay, now if I make a table with 2 columns in it, the first one is the actual, and the second one is the observed. 585. And if we take 2615 and divide it by 1, 2, 3, 4, 5, our expected value is 523. That's what we're expecting. And then we could go again to our calculator, stat tests, go to GOF, not the first one, the second one, L1, L2, perfect. Our degrees of freedom this time, since there's 1, 2, 3, 4, 5 cells, our degrees of freedom is going to be 5 minus 1 is 4. Let's calculate that. Oh, I must have done something wrong. Let's go back to stat. Let me go back. Oh, I know what happened. Stat, edit. I didn't put the values here. So there should be 523 in each. Oops, 523, 523. I got to fix that. Go back up here. Okay, now let's try it. Stat, test, go to the goodness of fit test. Degrees of freedom 4, calculate. Let's take a look here. Again, we have a very small p-value. Chi-squared is 47.5. Okay, I'll write that down. Chi-squared equals 47.57 with a p-value of practically 0. So you know what we'll do. We'll reject the null in favor of the alternative. It's not distributed the way we expect it to be. This is way too high. This is way too low. There's more variation than we would expect from just random selection. Okay, so this is how you would do this kind of problem. Let's go back to the M&M's problem for a minute, because what I want to show you there is what to do if you're not expecting a uniformly distributed chart. So here's what we have. We have the actual values and the expected values. So for the actual values, so we got brown, we got, oh, I'm going to squeeze it in there.